Next speaker is Garcia Castro from Santander in Colombia.
Thank you. Okay, good morning, everyone. Today I will present you some results on the direct magnetization-polarization coupling in the BaCuF4, in this family of materials. First, let me thank to the help of my collaborators, Eric Musquet at University de Liège, Wilfredo Ibarra at Benemérita Universidad Autónoma de Puebla, and Aldo Romero at West Virginia University. And of course, it's good to thank to the EXID for the computational support. Okay, so Bucaramanga is a city that is located here in Colombia, close to the border of Venezuela. It's a really nice city. You are more than welcome. And by the way, did you know that the largest number of species of birds and one of the largest moorlands in the world is in Colombia? So just a fun fact. Now that I catch your attention, look the colors. So now that I catch your attention, let's talk about physics. Okay? So in the quest for magnetoelectrics and multiferroid materials, we have been looking for several things and ways to couple polarization and magnetization. In this really nice review, these have been the mechanisms that supports the coupling or the coexistence of ferroid properties. One of them is the well-known lone pair in bismuth ferrite. We all have heard about it. The geometric ferroelectrics, for example, in the yttrium manganite, where the octahedra goes out or into the axis, and then the A side is the responsible for the displacement, and then the ferroelectricity is reached. There are another type of materials. The sodium manganese fluoride is one of the materials that we tested. It's the first magnetoelectric fluoride perovskite. First, it was predicted by us, and later was confirmed experimentally. And this family of materials and this family of oxides, layer oxides, I will comment about that later. And here, for example, in the charge ordering materials, the charge for the iron case, and when we have the 2+ and the 3+ charge ordering, it will arrange in a way that favors the polarization or the polar displacement. And these other type of couplings that have a strong magnetoelectric coupling, but the polarization is really, really small. The maximum that has been measured in this type of materials is 0.3 microcoulomb per centimeter square. Okay? So, however, the big problem here with the magnetoelectric crystals, it has been their scarcity, their small response, and their low functional temperature. Okay? So, when we look at the coupling on this type of materials and how can we design or enhance this type of coupling, we need to look at the magnetism. So when we have a look on the source of the weak ferromagnetism, we know that the Dioulowsinski-Morilla will depend, it was an antisymmetric interaction, and it will depend on this relationship. However, it requires a very, very specific symmetry conditions. Okay? So in perovskites, the polarization doesn't allow or doesn't favor the appearance of this type of interaction. However, the rotation does, as we all know. As we can see, for example, in bismuth ferrite, where we see the small canting of the spins, and if you check or you look the weak ferromagnetic canting as a function of the rotation angle, you will see that it increases according to this relationship. But at the same time, if you look the angle, but now you compute it through the relationship between the Dioulowsinski-Morilla constants of the tensor and the exchange constants, you will see that you reproduce clearly what you get from the unit. Okay? So, but again, here is the problem. So, one way that was designed to condense both properties together was through rotations, how I was saying, and through the improper ferroelectricity. And in this one, what it has been done is that to couple the polarization through the rotations, but polarization is a secondary order parameter in this type of coupling. Okay? So rotations induce polarization through the improper coupling, and it has been already exposed in these nice papers. The best candidates for this, it has been superlattices or double perovskites, where the A side is changed by a different type, and then we have uncompensated antipolar displacements, or in this type of materials, in layered perovskites, in the Dion-Jacobson, in the Lulzen copper, or in auridinus. However, there is a downside for this. And the only downside that we have seen up to now is that there is plenty of switching paths. So therefore, there is no entire guarantee that switching polarization, it will switch the mode that tunes the magnetization. And as we can see here, for example, in this figure from this paper, in here, you can tune, or you can switch, the polarization, but leave the magnetization untouched. So it was claimed that through a strain you can reach this energy landscape. However, depends on strain and on other conditions, so the balance between the energies and between the phonons is really smooth. And additionally, there is no guarantee of experimentally switchable polarization in this material, which was the prototype, at least at room temperature. So our idea was, we can go further, and the answer is yes, or we can try. And what we have done is to look carefully in the layer materials, but in this family, in the AN, BN, X3N plus 2. This type of materials is the same family such as the barium manganese fluoride F4, and for this one, N is equal to 2. Okay? In these ones, these materials have been already reported, experimentally synthesized, and most of them, and some of them, like in the nickel case, it has been already explained theoretically. And what we have in this type of materials, when we have N equal to 2, is that we have this type of structural arrangement where we have the octahedra here, and then we have the A side, which in this case is barium. So this is the supposed high symmetry structure, because this structure never reached the transition, has a function of temperature, and is really stable on the polar structure up to 1000 K. Okay? So the polarization is coming in here through this way. We have the rotations. Let's imagine that we have the rotations in this way, and when we have the rotations in this way, let's say that they rotate clockwise for this one, and then the barium goes to the right here. But when the polarization is switched, now we switch the rotations, and now the polarization goes the other way. Okay? So this is the perfect case, because in this polar phase, it combines rotation and polarization. And additionally, we have to mention that these two phases have been reported to be polar, but the switching haven't been reported yet. However, the switching in the nickel and the cobalt has been already shown, but there is no data for copper. And there is something special with copper that I will show here. And then additionally, there is no weak ferromagnetism for iron and the nickel cases, and for the cobalt as well, and only weak antiferromagnetism exists in the structure. But is it there for copper? So we try to look first on the literature, and this is a really nice paper. I have to train my French. It's in French. It's a really nice paper. And they synthesize this crystal in the 80s, and they measure the inverse susceptibility as a function of temperature, and they have observed that the nil transition temperature is really, really high, which is very interesting for fluorides, which has a really low temperature, and it has what we call A antiferromagnetic ordering for this type of materials. Compared to the other family of materials, the barium copper F4 is the only one that has this ordering. And what's going on here? So we can have these three different magnetic orderings for the unit cell. So in the layer we have two interactions. We can have this one, which we call for JC, and this one, which we call JA, and the interaction between the layers. So we can have full antiferromagnetic interactions. This one we call the G. For this one we have a ferromagnetic interaction along the x-axis, but we have antiferromagnetic interaction between this one and this one. And the other one is where we have the same ordering in all of the layers. Interestingly, this is the only ordering that allows the weak ferromagnetic contribution, the weak ferromagnetic moment, and is the one that has been observed experimentally. When we check the calculations, we observe clearly that this is the ground state of the system. So to remark here, we already know that we have a polar phase, and on top of that we have a weak ferromagnetism and an antiferromagnetic ordering that survives really close to room temperature. And what is the reason of that? So when we analyze more carefully the electronic structure, we can see that we have a strong Jahn-Teller distortion in here due to the D9 occupation of the copper, and we have a dx squared, x squared minus y squared type of orbitals. And look, for example, at the distances of the boundings for the copper and fluorine. This one is the longest one, it's close to 0.3, larger than the other ones, and that explains the magnetic ordering on this structure. And additionally, when we compute the exchange constants, what we realize is that the exchange constant along this direction is really strong, explaining as well the large antiferromagnetic Neal temperature. Okay, so we wanted to go a little bit further in the analysis of this material, and we try to understand better the switching of the weak ferromagnetism through depolarization. And to do that, we computed the phonons at the supposed high temperature structure. This one, I mean, it cannot be seen clearly, but what we observe here is that we have three different branches that are unstable at Y, S, and gamma. And these ones corresponds to different rotation patterns, okay? So, for example, when we look at the rotation pattern at Y, we can have this type of rotation pattern in which in the layer we have one rotation, one octahedra that's going clockwise, but the one on the bottom of it is going counterclockwise. And we have all these one through the entire structure. When we look at this phonon, what we see is that in the entire layer we have the same contribution, but these one go the opposite side, such as kind of similar to the one that we observed for the magnetism. They look more or less the same. But now when we look at the polar one, what we will observe here is that they rotate at the same direction through the entire material, okay? And when we see that, is that interestingly from here what we can extract is that rotations and polarization are entangled in a single polar mode, which is what we are looking for. And then it contains rotation and polarization, as already said, but there is no need for the proper kind of coupling in the material. So we won't have this downside, like we can, for example, have different rotation, have different switching paths in which we rotate the structure but we leave the polarization untouched, or the other way around in which we rotate or we switch the polarization but we leave the magnetization or the weak magnetization untouched. Okay? So what we did next is to check more carefully what happened when we switch the polarization, okay? So first, we look very carefully here. Oh, I forgot to mention, of course, that in these ones, the difference in energy corresponds, of course, to the ground state as reported experimentally and as we already observed, okay? So when we look, for example, at the classical or the typical double well, what we will observe is that we have a rotation. I mean, we have when we freeze or we condense the single polar mode, when we condense the single polar mode from minus 100% to 100%, we have a classical double well shape when we look at the energy or the difference in the energy with respect to the high symmetry structure. Now, when we look at the polarization, we see clearly the switching of the polarization, which is close to 11 microcoulomb per centimeter squared. But now, when we look at the rotation, exactly we have what we expect, the full change on the rotation. Now, if we look at the magnetism and the weak ferromagnetic component, which is close to 0.0706, we have the full switching of it. In here, we can see that we have the magnetic moment and the orbital moment. We just extracted to see if there is there was a strong contribution from it. It's not that strong, but the most important one is M. But when we switch the domain, and that's something that I will show later, we can see that we can have the opposite behavior. So we go from negative to positive through switching the polarization. So what does that mean? That is, we believe that it would be really, it's really important and it's kind of perfect coupling of the polarization with the weak ferromagnetic component, with the weak ferromagnetic moment through the rotations. And when we look at domains, here I took a kind of small snapshot of just one layer, because we know that all the layers have exactly the same rotation pattern and the same magnetic structure, okay? So this one is the one that we have already, which is the perfect one, and we go from M plus, P plus to N minus, P minus, okay? In this one we can see clearly that the canting is to this side, so we have a component through this, along this direction, and here as well, and here as well, and in here we have the switching. If we are able to switch the antiferromagnetic domain, that's something that it requires a lot. It's very easy to say and more difficult to do, but we would be able, or that's what we expect to have these other two multiferroic states, in which we have N minus P plus and N plus P minus, okay? So, but there's one question that remains, and it's something that I attract my attention, is it can be switched, because it can happen. It can have the same problems such as in the manganese or in the iron case. So one thing that we did is try to analyze the trend through the entire family. Okay, so in here we condense the members, known members, synthesized experimentally of the family, and I organize them through. I organize them by the radii of the B side. Okay, so for example, for the nickel case, we have 83 picometers, and when we are in the manganese, we have 97. Okay, if we look at the polarization, there starts to increase linearly. So if we plot this, you will realize that it's a perfect line going up, and then it goes down, it drops the polarization, and then it starts to go up again in the copper case. Okay, so that's exactly what we expect from a geometrical ferroelectric. However, when we look at the switching, these two members have been experimental report to be real ferroelectrics, and these two. This one, they are not, they haven't been switched, and the copper, when we analyze where is it in the table of the family, so probably it can be switched, but that's something that we hope some experimentalists will test. Again, to remark then, in the improper couplings, what we have is this type of expression where the polarization is coupled with the rotations. However, when we have in BaCuF4 or in all family of the materials, it's that the rotation and the polarization is entangled in a single mode, which is the perfect one for this type of applications. And then there is no other choice that flipping the rotation when we flip the polarization. Okay? And in here there has been, reported some ferroelectrics, layer ferroelectrics, and possible multiferroids that we can look for. Okay? So as a general remarks, we know that the BaCuF4 has an ideal polarization and magnetization coupling. It doesn't require from the improper coupling. Okay, so that's really interesting. It's already a close to room temperature multiferroic, in which the Néel temperature is close to 270, and the Curie temperature for the ferroelectric ordering is close to 1000 K. Okay, and is the unique candidate? That's something that we need to ask, and the answer is no. There is these three families of materials where we can have the same coupling of the rotation and the polarization. And I invite you to look at this really nice paper. It's a paper around 70 pages long, nicely synthesized crystals and characterized in the oxides family and fluorides. And thank you for your attention.
Paper is open for discussion. Any question for the audience?
It's a very nice proposal. I'm not sure I understood what was the energy argument or energy scale which prevents or allows you